Well, the binomial random variable, okay. And so this is a good opportunity to review what the heck that is. Okay, so remember, the binomial random variable x is the number of successes in n independent trials with success probability p in each trial. Okay, so very important random variable. Okay, so you're trying something and you're going to try n times. For example, you're going to randomly answer the multiple choice in the test. Don't do that. Okay, we analyzed that last time. Don't do it. Okay, so you try something some number of times, n times. Okay, and each time has a success probability p, and you're interested how often, how many times did I succeed? How often did I succeed? Okay, and a trial with success probability p is exactly a binary, a Bernoulli random variable. So this is exactly, each of these are exactly a binary Bernoulli random variable, which can either equal 0 if you fail or 1 if you succeed. So a binomial random variable is exactly the sum x1 plus x2 plus x3 plus up to xn. It's exactly the sum of n Bernoulli random variables, each with success probability p. Okay. Now, just as with the example of dice, where if you roll one die, your expected roll is 3.5. If you roll 2 die, it's 7, and then we guess that if you roll 3 die, it's 10.5. So you're doing the sum of, instead of die, of a Bernoulli flip, and so and since each of these has an expected value of p, which we just computed, you might guess that the expected value of x is equal to p plus p plus p plus p, which is np. You might guess that. But you're not going to allow me to get away with a guess. This is a math class, so we'll actually now compute that. Okay? But it's a very intuitive answer that pops out. Okay? So if you try something n times, and each time you succeed with probability p, then the expected number of successes is n times p. Wow, what an intuitive result. Okay? Well, let's actually derive it. So what's the Bernoulli random variable? So the possible values are, when you try n times, and you can either succeed 0 times, 1 time, 2 times, 3 times, all the way up to n times. Okay. Now what's the probability of k successes? The probability, so p sub x of k, let's call it k successes, is, n choose k, p to the k, 1 minus p to the n minus k. So we derived this last time. It's a complicated formula. Look at that. Wow. Okay, so here the probability is n choose 0, okay, p to the 0, 1 minus p to the n. Okay, and then n choose 1, p to the 1, 1 minus p to the n minus 1. Okay, and then so that's 0, that's 1. Let me place this. Let me write this as 1. Then 2. The probability of getting 2 successes is n choose 2, p to the 2, 1 minus p to the n minus 2. And 3 would be n choose 3, p to the 3, 1 minus p to the n minus 3, and so on. N choose n, p to the n, 1 minus p to the n minus n, which is 0. Okay, so complicated. Okay, but that's what I said. Computing expected values, in principle, conceptually, is very easy. You weight each possible value by its probability and add. Just get that into your heads. That's all it is. It's a very simple conceptual idea. Weight each possible value by the probability and add. Okay, that's what you should be thinking, and interpret it as, when you repeat the experiment many times, on average, what's the average that you will see? Okay, so sometimes this sum is a complicated sum. Oh well. Okay, so we weight. So we weight this by the probability, weight this by the probability, weight, and then add. So we have the expected value of x is equal to n choose 0, 0 times n choose 0, p to the 0, 1 minus p to the n, plus 1 times n choose 1, p to the 1, 1 minus p to the n minus 1, plus 2 times n choose 2, p to the 2, 1 minus p to the n minus 2, plus n choose n, p to the n, 1 minus p to the n minus n. Okay? And, when we look at this sum, we have to compute this sum. It looks very daunting, so let's simplify a little bit. Let me call, and it's often the case that you will see this done, let me call this guy Q. Okay, so let me call this guy Q. So this is that Q equals 1 minus P. Okay, so then the expected value of X, okay, is equal to 0, n choose 0, p to the 0, q to the n, plus 1, n choose 1, p to the 0, p to the 1, q to the n minus 1, plus 2, n choose 2, p to the 2, q to the n minus 2, plus plus n choose n, p to the n, q to the 0. Okay, well, technically I should put here n minus n. Okay, now I want to remind you of a formula that we derived, and we derived it from a counting argument, but this is a very famous formula. So it's the binomial formula. So p plus q raised to the power n is equal to, okay, and so I'll state the formula. Sum from I equals 0 to n. N choose I, p to the I, q to the n minus I. And you should see a very strong resemblance between this guy and that guy. Okay, they're basically the same, okay, with I taking on the role of k and q taking on the role of 1 minus p. But let me write this out. So this is equal to n choose 0, p to the 0, q to the n minus 0, plus n choose 1, p to the 1, q to the n minus 1, plus n choose 2, p to the 2, q to the n minus 2, plus n choose n, p to the n, q to the n minus n. Okay? And well, this long complicated sum and this long complicated sum are very similar, except for the 0 here times that, and the 1 times this, and the 2 times that, and so on and so on. And there should have been an n times this. N times this guy, okay, and n times that guy, okay, because you multiply n times this, okay, when you're adding. Okay, so if not for these guys, this whole sum would equal this whole sum, okay, and that would equal this very simple expression. Okay, so now here's a trick. Whenever you see the numbers, 0 associated with some variable to the 0, 1 associated with a variable to the 1, 2 associated with a variable squared, n associated with a variable to the n. I will remind you that the derivative with respect to p of p to the k is equal to k p to the k minus 1. Okay, so if I take the derivative, so now think of q as some fixed number, and I'm letting p be a variable. So let's take the derivative d by dp on both sides of this equation. So on this side of this equation, so q is a fixed number, so p is the only variable here. So d by dp, okay, I'm going to get here n p plus q to the n minus 1. Okay, and that's going to equal, so the derivative with respect to p, this doesn't depend on p, so I get 0. Well, 0 times, which is just a constant 0. 0 times p to the, 0 minus 1, which is, derivative of a constant is 0, plus 1, okay, n choose 1, p to the 0, q to the n minus 1, plus 2, okay, n choose 2, p to the 1, q to the n minus 2, plus plus n choose n, p to the n minus 1, q to the n minus n. Okay. So where did this 1 come from? This 1 came from the derivative of p. So the derivative of p raised to the power 1, according to the standard formula from calculus, is 1 times p to the 0. The derivative of p squared is 2 times p to the 1. The derivative of p to the n is n times p to the n minus 1. So if I take the derivative of the right-hand side, it had better equal the derivative of the left-hand side. Okay. So now I'm comparing this formula to that formula, and I see that I've gotten my, okay, this term is 0, I've gotten my 1, I've gotten my 2, and so on, I've gotten my n, but now I have another problem. I didn't solve anything, it looks like, because here I had 1 times p to the 1, here I have 1 times p to the 0, here I have 2 times p squared, here I have 2 times p to the power 1, here I have n times p to the n, here I have n times p to the n minus 1. Okay, but you'll observe that each term here is just missing one factor of p. So now let me multiply by p. So I get np, p plus q to the n minus 1 is equal to, okay, 0 times p is 0, plus 1 times n choose 1, p to the 0 times p is p to the 1, q to the n minus 1, plus 2, n choose 2, p to the 1 times p is p squared, q to the n minus 2, plus, plus n choose n, p to the n minus 1 times p is p to the n times q to the n minus n. And now, if I compare, I see that I have exactly that expression. Okay, 0 plus 1 times n choose 1, p to the 1 times q to the n minus 1, 2 times n choose 2, p to the 2, q to the n minus 2, and so on. I'm really tired now, but we're done. Look, because that means that this sum is equal to this, and this sum is equal to that. So that sum must equal this. Conclusion, the expected value of x is equal to n p plus q to the n minus 1. That's a trick. Wow, that came out of nowhere. Okay, but now we know that q is 1 minus p. Okay, so p plus q is just 1. This is just 1. So this is np. Bam! And I derived it. What we guessed has been derived. Okay, so that's comforting. The guess is just a guess, but we have now derived it using the definition of the expected value, and it involved a complicated sum. Okay, complicated sum. Well, we can do sums. We're strong. Okay, now let's take an example. Remember, we did this example. You had a test. So example. So you have a 15 question test, 15 question test. Okay, and on each question you randomly guess if there are 5 answers. So you randomly guess. So randomly guess. So that means the probability to be correct is 1 over 5. So that's the probability of success, and you have 15 trials. You have 15 trials. The probability of success on a trial is 1/5, and you want to know that's a binomial random variable. You try 15 times independently, each time 1/5 success. So p is 1/5. So n equals 15, p equals 1/5. So the expected number of questions you get correct, expected number correct, is equal to 3. Okay. So now let me tell you again. Let me just re-emphasize. The expected value is a formula. It's a formula that summarizes the experiment. It's not a typical value or what you might incur when you run the experiment and make the measurement. It's a summary of the experiment. It tells you, okay, what will happen if you run the experiment many times and take the average of the outcomes, the average of the measurements. Okay, so if you do such a test many times, on average you will get 3 questions right. It's a summary of the experiment, and that's very important. So we start with a complex experiment. We summarized it by looking at the quantity of interest, the measurement, okay, and that was a random variable and its associated PDF. And now we have further summarized the experiment by sort of condensing the entire PDF to a single value. Okay, the expected value. It's another summary of the experiment. You can think of it as what do I expect will happen, but technically it's what will happen on average. Okay, what's the average outcome? Okay, let's erase and do the waiting time. Bam, bam, bam.